I'm Casey. I'm Casey Lyons. I'm presenting for the red team over the filter wash pump system. We're going to cover the SSOC, the step, and the frequency response. And an outline is the system background, the steady-state operating curve, the transient flow, which is the step, and the frequency response. Background, the system is a simulation of the sewage treatment plant in Chattanooga. It separates sludge from landfill storage. Wash water is used to clean the filter. For ours, both the valves are closed, so it just goes from the pump into the filter washing nozzles, and then outputs our data. We have a motor input in percent, which goes into the filter wash pump system and outputs water flow in pounds per minute. The objectives of the SSOC was to observe the step response and to get the gain, the time constant, and the dead time for the step response. This is an example step response where this was our steady-state operating curve. That would be for, looks like about somewhere in the middle range, or that's the lower range, I'm sorry. Where this is our steady-state operating curve, where the low range is from 20 pounds per minute to 27 pounds per minute, and that was between 65 and 75 input percent. And then the middle goes from 27 to 33, and the high goes from 33 to 38. For the transient flow, we have to do an input baseline, an input step for each of the different low, mid, and high ranges. This is for a 65% base, which outputs around 22 pounds per minute and goes up to 27 pounds per minute. So that would be the lower range. And you can see that's the delta M is your change in your input percent, and then your delta C is your change in your output pounds per minute, and then the TO is the dead time, and the tau is at 63.2% delta C. This is the equation for the FOPDT model that we used to model the step. And this is an example model of the step. Same values as earlier for the lower range. And as you can tell, the model worked out pretty good. This is the data for step up, step down, step up, and step down for low, middle, and high ranges using the visual and the FOPDT. That's for the gain with the uncertainty bars. And then that is for the dead time, where they're all pretty close. And then that is for the tau, which for the lower range was a little bit lower, but for the rest of them worked out pretty well. The average gain for the system for the step response was 0.48. The average dead time was 0.44, and the average time constant was 0.8. This is for the frequency response at a frequency of 0.3 hertz, an amplitude of 7%, a baseline of 81%, which goes from 27 to 33 pounds per minute, which is the middle range. And the delta C is the change in the output, where the big T is the time difference between the two peaks of the input, and the little t is the dead time or the lag time from the input peak to the output peak. The phase angle and the amplitude ratio can be found once you find these values, where the phase angle is little t over big T times 360 degrees, and then the amplitude ratio is delta C over delta M, which is your change in output over your change in input. This is the Bode plot for the middle range, and it shows how graphically or experimentally you can get these values. This one had an ultimate frequency of 0.53 hertz, an order of 1.44. The 1 over KCU is 0.3, which will give you 3% per pound minute, and then the gain of the system was 0.68. For modeling the phase angle and the AR, these are the equations that we used, where omega is 2 pi times our frequency, which is what we inputted. This is the Bode plot for AR for the mid-range, and you can see it fit pretty well, except for at the end it kind of dove off. And this is for the phase angle for the mid-range again, and this was gained by manipulating the dead time value. That's for the high range, 33 to 38 pounds per minute, and it turned out about the same. And this one was for the low range from 20 to 27 pounds per minute, and it also turned out to fit pretty well. This is the values for gain for the 3 different ranges, and they worked out pretty well. For the high range it was lower, but for the low and mid they were almost exactly the same. For the dead time, it got a little bit smaller as we went up in our range, but other than that, they're still pretty close. They're within 1/10 of each other. The response time was lowered as we went up in range, and but they were still within 2/10. The FU increased the same as the response time did. Not the response time, the dead time did. It had the same pattern. The KCU was high for the high range, but for the mid and low range was really close. And the order was almost exactly the same for all of them, which was about 1.45. The average values for the system, for the frequency response, the gain was 0.6, the dead time was 0.62 seconds, and the response time was 0.52 seconds. And then those values were used to model our system, where the red is the output, the actual output, the blue is the input that we inputted. There's a little orange line, probably hard to see, but that's the input model, and then the green is the output model for a frequency of 0.05. That's it.